Hello and welcome back. In my last video I introduced the concept of group homomorphism. So what is that? Which is a mapping. So suppose we have two groups, so let me recall that. So recall the definition of group homomorphism. So suppose we have two groups, one is G with a composition and another is another group with another compositions, and a group homomorphisms between G and G dash is a mapping. So is a mapping satisfy the property that phi of A compose B, which is same as phi of A compose phi of B, and it is true for all elements in the group G. When this property is satisfied, then this mapping phi is called a group homomorphism from the group G to the group G dash. So in this direction, here we have a few more definitions. So few more definitions in this direction. Definitions. So a homomorphism. So let phi from G to G dash be a group homomorphism. Be a homomorphism. Now, because phi is a function, we can talk about the one-to-one function, one-to function, and so on. So if phi is an one-to-one function, if phi is one-to-one, so if phi is so and one-to-one mapping, so one-to-one homomorphism, so homomorphism on that case is said to be a monomorphism. If phi is an one-to-one homomorphism, then we will call, then phi is said to be monomorphism. Here are few definitions you have to remember. So this is called monomorphism. Now, because again phi is mapping, we can talk about the phi is one to or not. So if phi is an onto homomorphism, is an onto homomorphism, which means phi is an injective map. So onto homomorphism, then we will set to be, then phi is said to be, epimorphism. Then phi is said to be epimorphism. They are the name for different type of homomorphism. So one-to-one homomorphism is called monomorphism, monomorphism, and onto homomorphism is called an epimorphism. Now this mapping can be one-to-one and onto at the same time, which means if phi is an bijective homomorphism, on that case phi will be called isomorphism. So let me write that down. So if phi is a bijective homomorphism, then it is called, so bijective homomorphism is called, and so bijective homomorphism is said to be isomorphism. So they are different name for different type of homomorphism. So I think you remember this name for different type of homomorphism. Okay, let's go to the another example. So let me give an example of homomorphism. So last day I talk about a few more example. Today I going to talk another example, and from there we will go to the some results related to homomorphism, or especially to isomorphism. So first of all, let me talk about results. So before that we're going to talk about an example of group homomorphism. So suppose we have two groups. So let G with a compositions and G star with another composition be two groups. So let me write down 1 and B2 group be two groups, and if EG dash, so if let me write down and let again that EG dash be the from now on basically. So do not I do not want to write in the example. So from now on what we're going to write, EG, by EG we denote the identity elements of the group. So identity elements, so identity of G, and EG dash, by EG dash we will going to mean denote that the identity of the group G dash. So in this way we will differentiate the identity elements of different group. So here we go. So let me define a mapping. So if I defined a mapping in this way, that phi from G to D dash is defined in such a way that phi of A, all elements of the group A going to be identity elements of the group G dash. So this is, we define the mapping. So all elements is going to, so suppose we have a set G over here, and we have the set G dash over here, and we have the identity elements over here. So all elements of G basically map to the same elements G dash, EG dash. So in this way the mapping is defined. So is this a homomorphism? So let's check that this is a homomorphism or not. So what we have to do, we have to take two elements. Let A and B are two elements, any two arbitrary elements of G. So what we're going to do, first we compose these two elements, so we get A compose B. Now we're going to transfer these elements by this mapping, so we get phi of A compose B. Now each and every elements of G going to the identity elements. So because phi A compose B is an element of G, so this also going to be to the identity elements of G dash, by this because the mapping is defined in this way. So now what about the elements A by the mapping? So it goes to the elements phi of A, and from the definition is always going to the mapping EG dash. Similarly B by this mapping phi going to the elements, so they are going to the elements phi of B. Now phi of B is obviously again EG dash, because all our elements of G are mapped to the one and only elements, the identity elements of G dash. So now what about phi of A compose phi of B, which means we are composing EG dash with EG dash, because EG dash is the identity elements of G dash is going to be EG dash again, because the composition of two identity elements is again identity elements. So we get the identity element which is phi of A compose B. Now it is true for any two elements A, B and G, because we choose A, B are any two elements, so they are arbitrary on that sense. So we have seen that this property is followed for the elements A, B. So phi is an homomorphism. So phi is a homomorphism. Now is this an epimorphism? Obviously not. If G dash contain more than one elements, this is not going to be an epimorphism. So suppose, so is this, you may ask two questions: is this an epimorphism? Is this a monomorphism? Epimorphism and monomorphism, both of them together implies an isomorphism. So let me write that first. So 1 to 1 and on to implies bijective, because 1 to 1 and on to. So because let me before that let me write 1 to 1 plus on to implies bijective. So here we have epimorphism, sorry, for 1 to 1 we get monomorphism. So monomorphism plus epimorphism together implies, or together equals to isomorphism. So if one of them is missing, if at least one of them is not satisfied by a homomorphism, then it's not going to be an isomorphism. So the first task is to check is this a monomorphism or not. So you can see that if G has two different elements, it's suppose G is a group and we are taking a group G with more than one element, so G is greater than two elements, and also the order of G dash is also greater than equals to 2. If I choose in this way, if I choose our group that which contains not only the identity elements, so except identity elements we have a non-identity elements. Similarly, if G dash contain a non-identity elements, then we have two elements A, B of G, for which an A and B are different because G contain more than two elements, more than one element, so it may contain two elements, and but phi of A equals to phi of B, which is the identity elements of G dash. So we get for the two elements of G we get the same value, so phi is not an 1 to 1. So phi is not 1 to 1. So phi is not a monomorphism. Phi is a homomorphism, but it is not a monomorphism. So is this epimorphism? So if G dash contain more than two elements, so if G dash contain more than two elements, then obviously we have an elements A dash, which is obviously not equals to E G dash in G dash. So but there is no elements in G. So suppose we have an elements A over here, and you can see that no elements map to the elements A. So no A belongs to G, so that phi of A going to be mapped to the elements A dash. So phi is not onto map, phi is not onto, so phi is a homomorphism but not onto, hence is not an epimorphism. So this is not neither a monomorphism nor epimorphism, so it cannot be an isomorphism. So this is one of the example, which is example of a group homomorphism which is neither monomorphism nor epimorphism, and so no isomorphism. So this type of group homomorphism, where all elements map to the identity elements of this codomain sets, so this type of homomorphism is called a trivial group homomorphism. So this is called, so remember the name, this is called a trivial group homomorphism. So this is the name of this type of map, where each and every elements of a group map to the identity elements of the group G dash. So in this way we can talk about the group homomorphism. So let me give you some quick results in this direction. So let me erase these parts and let's talk about results. So today I only prove one results, and from next day we will go with other few results in this direction. So first of all, let me talk about our results. So here we go. So before that I have to erase these parts. Sorry, I have to take time to erase these parts. Yeah. So here we go. So here is the results. It's a very important results in group homomorphism. So it results 1. So it says that if let two groups, let G with the compositions and G dash with another compositions are two groups, be two groups and phi and phi from G to G dash be a homomorphism, then we have these results. Then it says that the identity elements of the group G always goes to the identity elements of the element G dash. So identity elements of one group always map to the identity elements of another group. This is a very important results in the chapter of group homomorphism. So identity element of one group always map to the identity elements of the other group. So let me quickly give you the proof of these results. So what we know, so because EG is an identity element, so we can write EG compose EG is EG. Since let me write since EG is the identity elements, is the identity element, so element of the group G. This is from the property of identity elements. EG composed with EG always give EG. Now phi is an homomorphism. So since phi is an homomorphism, before that we take the mapping. So that means before, because this quantity is equal to this quantity, so phi of EG compose EG is same as phi of the identity elements. They are same, so their function value they are going to map with to the same elements. Now phi is an homomorphism. So now phi is an homomorphism. So we can write. So here we have awkward notation. So here we can write. So because phi is an homomorphism, we can write phi of EG. Now the composition of G star, so EG, which is equals to phi of EG, because since phi is an homomorphism, since phi is homomorphism. So which property we use for homomorphism? Because any two elements A compose B, which is going to be phi of A star phi of B, so we use this property over here. So here we have this A and B, which is phi of A star phi of B. We use this property. Now what we going to do over here, we going to, because we can write, because EG dash is the identity elements of the group G dash, so we can write EG star phi of EG, which is equals to phi of EG star. We can write EG dash because EG dash is the identity elements of the group G dash, and we know that if I compose with any elements, with the identity elements, we get the same elements. So EG star EG dash we can write, because if I compose with this, we will get these elements. So because let me write over here that EG dash, because since EG dash is the identity elements of the group G dash, so EG dash, since EG dash is the identity elements, of the group of G dash. So from now, what these elements has an inverse elements, so we will going to take the inverse of these elements both side. So take the inverse. So let me erase this part and write this line in upper part. So from there, what we can do over here, we don't have the penalty of space. So that's why we have to erase the each and every parts and write that down. So what we get from there, we get phi of EG star phi of EG, which is equals to phi of Eg star Eg dash. Now we're going to take the inverse of these elements. So inverse of these elements, so phi of Eg whole inverse, so phi of Eg whole inverse composed with phi of Eg. Now because the group is operation is associative, so we can write in this way. So phi of Eg and phi of Eg, both side I am taking the inverse both side. So phi of Eg star phi of Eg star Eg dash. Because associative we can take the bracket from in this way you can take the bracket, because the group operation star is associative, so we can do this. Now Eg and Eg going to gives us the identity elements, so we get Eg dash star phi of Eg, and here we get also this going to gives us the identity elements, so Eg dash star Eg dash. So now Eg dash, so from there we get phi of Eg, because if I take composition with identity elements we get the same elements, from also we get the Eg dash. So phi of Eg dash is the identity elements proved. So that's how we have to prove this result. So this is one of the results in the chapter of group homomorphism. So in my next video I will talk about a few more results in this direction. So please come back in my next video, and thank you for watching.